Hey, we've got a really nice integral here today from the UNSW Integration Bee. We have the integral from 0 to pi over 2 square root of tan x dx. Okay, to start, what I want to do here is some kind of u substitution, and I want to use these bounds. The nice thing about the bounds from 0 to pi over 2 is we can do a substitution that's going to allow us to use the complementary angle formula. Okay, what I'm going to do is we're just going to make our u substitution for the sum of these bounds, pi over 2 minus x, and then from that we can rearrange that real quick and we can see that x is going to be pi over 2 minus u. I'll get my dx value by taking the derivative. The pi over 2 is going to be 0. We're going to have minus du here. So let's make our substitution and see what we have. So we're going to plug in pi over 2 here. So for our upper bound, we'll have a 0. And then plugging 0 in, we're going to have just pi over 2. Then we'll have the square root. We're going to have our tangent. Plugging in x, we're going to have tan pi over 2 minus u. And we're going to have minus du here. But what I can do with this minus sign, I can bring it out front here and use to flip my bounds. But I think rather than rewrite the whole thing, I'm just going to do that. So we'll just rewrite this over here. And then like I mentioned earlier, this complementary angle formula is very useful here because this thing here, tan of pi over 2 minus u, is going to be the same thing as just cotangent of u. So what I'll do is I'll rewrite this, but what I'm going to do, I'm looking to get back something similar to what we had originally. So what I'm going to do a variable change. Because it's a definite integral, there's no problem with me changing my variable. So what we'll do is we'll change this all back to x, and we'll just do the rewrite. Then from here, what I'm going to do, we're going to call, just notice our original integral, we'll call it I, and then that means that this here is also I, and we'll just add these two together. This is typical of how we handle like the King's principle. So we'll get two copies of the integral. So for our 2I, okay, again, as we have the same bounds and we have the same variable, we're allowed to add these two together. So now we've done that. Now this is where it gets a little bit different than like a typical King's principle problem. Typically with the King's principle problems, it's like a rational function, and at this point we just have one. But now we're adding the square root of tan x plus square root of cotangent x. It's not clear how this is going to simplify. So then for my next step, what I'm going to do is I'm going to just turn this into sines and cosines and see how that goes. And then from here, all I want to do is I just want to get a common denominator so I can put these two together. So basically here, we're going to be multiplying by a square root of sine x over sine x on a less base. We'll just do it like that for now. And then here, we're going to multiply by square root of cosine, square root of cosine, in order to get this common denominator. We put these two together with square root of sine x cos x in the denominator, because here we had a sine squared in the radical, and here we had a cosine squared. We just end up with sine x plus cosine x in the numerator. Okay, now here's where it gets a little tricky. It's not quite clear what we do with this integral, but there are some insights we can have. So you can see that this isn't the right form to use like the double angle formula. It's almost like we could write this as half sine 2x. But that doesn't help us that much as far as trying to simplify it. So what I'm going to do next takes a little bit of like a leap of faith, because it's kind of what I want to happen here is I would like to do a u substitution of sine x minus cosine x. And the reason I say that is let's just look what happens. Look at what our du is going to be. The derivative of sine x is going to be cosine x. The derivative of minus cosine x is just sine x. So what would happen, if we can do this substitution, okay, then our numerator is just going to be du, and that's going to be nice. Now the only problem is we don't have this sine x minus cosine x anywhere in the denominator. So what I want to do is kind of create this. I want to see if I can create a sine x minus cosine x somehow out of this piece right here. Let's look at how this is going to work. I'm going to take my sine x minus cosine x, which is just our u, and we'll square that and we'll multiply it out. When we do that, we get a little bit of magic because we get sine squared x plus cosine squared x minus sine x cos x. Because sine squared x cosine squared x is just 1, we can rewrite this as 1 minus sine x cos x, which is the thing we want to focus on here. So all we really need to do is just a little rearranging in order to make this work. We can bring this on the other side of the equation, and we can write this as sine x cos x equal to 1 minus this thing, but this thing's just u squared. Sorry, I made a mistake when multiplying it out. This is actually supposed to be a 2 here, and a 2 here, and a 2 here. But what I can do with this too is I'm going to actually divide it right here. Okay, so now I'm ready to make this substitution. Okay, so first I'm going to update my bounds. I'm going to plug pi over 2 in here. Sine of pi over 2 is 1. Cosine pi over 2 is 0. So for our upper bound, we're just going to have 1. And then plugging a 0 in. Sine of 0 is 0. Cosine 0 is 1. Our lower bound is going to be minus 1. Then again, like I mentioned earlier, the whole numerator is just going to be du. We set it up that way on purpose. Inside the radical, in the denominator, we're going to have 1 minus u squared, but we're going to have this 1/2 out front. Just to clean this up a little bit, I don't like this half here, so I'm going to pull this out, and we're going to write that as the square root of 2 out front. Then one other thing before we integrate this, noticing this is an even function, I can just change this lower bound to a 0, but I need to bring a 2 out front. And that's pretty good because remember this whole thing is 2i, so I'm just going to cancel a 2 with that. So now we're just finding this as the value for our full integral. So because this is arcsine, all we need to do is evaluate this arcsine from 0 to 1. Well, that's pretty easy. Arcsine at 0 is just 0, so we're not going to worry about that, but we're going to have our square root of 2. Arcsine of 1 is actually pi over 2. So we could leave it this way. I think the way they had it in the answer key was pi over square root of 2. That was a pretty fun problem. Hope you enjoyed it. Thanks everyone for watching. Please like and subscribe. Have a great day.